Welcome to our channel Circuits Analytica. In this video, we will discuss the operation of an ideal integrator. This is the circuit diagram of an ideal integrator. Basically, an integrator is an inverting amplifier. The non-inverting input is connected to ground and input signal Vin is applied to the inverting input of the operational amplifier through resistance R1. Capacitance Cf is connected between the output and the inverting input of the operational amplifier. Concept of virtual ground. For an ideal operational amplifier, open loop gain AOL is infinite. AOL is nothing but output divided by differential input voltage VID. AOL is infinite means VID is equal to 0 mathematically. So VID is the differential input voltage and it is defined as the difference between voltage at the non-inverting input and voltage at the inverting inputs. So we can write VID is equal to V1 minus V2. VID is equal to 0 means V1 minus V2 is equal to 0 or V1 is equal to V2. For an ideal operational amplifier, voltage at the non-inverting input is same as voltage at the inverting input. That means V1 is equal to V2. In the case of an integrator, the non-inverting input is connected to ground. That means V1 is equal to 0. V1 is equal to 0 means V2 is also equal to 0. And this condition is called as virtual ground. Now let us analyze the operation of an ideal integrator. So applying KCL at the inverting input of the operational amplifier, we will get In is equal to If plus current flow towards inverting input of the operational amplifier, which is equal to 0 for an ideal operational amplifier. Therefore, we can write In is equal to If, equation number 1. Now let us find In. In is the current flow through resistance R1, which can be written as voltage drop across resistance R1 divided by R1. Voltage drop across resistance R1 is equal to Vin minus V2. Therefore, we can write In is equal to Vin minus V2 divided by R1. As V2 is equal to 0, we will get In is equal to Vin divided by R1, equation number 2. Now let us find current flow through capacitance Cf, feedback current If. So we know that generally for a capacitance, current flow through that capacitance is equal to C into dVc by dt. So here we can write If is equal to Cf into dVc by dt, where Vc is the potential difference between the two terminals of the capacitance. So If is equal to Cf into dVc by dt. And Vc is equal to V2 minus V0. As V2 is equal to 0, we will get Vc is equal to minus V0. Therefore, we can write If is equal to Cf into d minus V0 divided by dt, or If is equal to minus Cf dV0 by dt, equation number 3. From equation 1, we can write In is equal to If. Now let us equate equation number 2 and equation number 3. We will get Vin divided by R1 is equal to minus Cf into dV0 divided by dt. Rearranging the terms, we will get dV0 is equal to minus 1 by R1 Cf V in dt. Now integrating both sides, we will get V0 is equal to minus 1 by R1 CF integral V in dt. So here output of the integrator is proportional to integral of the input signal, so the name integrator. Now let us discuss the operation of the circuit. For DC signals, capacitive reactance CF is equal to 1 by 2 pi Fc. F is equal to 0. So for DC signals, capacitive reactance is equal to infinity. As capacitive reactance is equal to infinity, the circuit behaves as an open circuit. So depending upon the polarity of the input voltage, we will get either plus Vsat or minus Vsat at the output. Suppose input Vin is negative, then output is equal to plus Vsat, and if input Vin is positive, then output V0 is equal to minus Vsat. At very low frequencies, capacitive reactance is very high, and as capacitive reactance is very high, output voltage is maximum at very low frequencies. So the circuit behaves as an open circuit. Depending upon the polarity of the input signal Vin, output voltage will be either at plus Vsat or at minus Vsat. If Vin is positive, output voltage will be at minus Vsat, and if Vin is negative, output voltage will be at plus Vsat. When frequency of the input signal is increased, capacitive reactance falls. When frequency of the input signal is increased, capacitive reactance XCF falls, so output voltage reduces gradually. And when input frequency is very high, capacitive reactance acts as a short circuit, so output voltage becomes 0. This is the frequency response of an ideal integrator. Initially, when frequency of the input signal is equal to 0, or for DC signals, the output voltage is plus Vsat, assuming that input voltage is negative. And when frequency of the input signal is increased gradually, output voltage becomes 0. Thanks for watching Circuits Analytica. Enjoy learning.